whatever you want. Still, this is not allowed for the moment, right?
I don't know why I'm so nervous, but well, it's okay.
Go ahead.
Okay.
Yeah.
So it's done. Okay, hello everyone. My name is Borja and I'm going to give a presentation about what we have been working on, which is a deep learning model for the detection of carbon-13 nuclear spins. First, I'm going to describe a little bit this problem so you can get a general idea about what we are talking about. So carbon-13 constitutes about 1.1% of carbon in diamond and in general in nature. And when we have an MV sensor placed in a diamond, this sensor is coupled to each one of these carbon-13 nuclei with a dipolar coupling A. So the goal of this work is to analyze how many nuclei are coupled to this sensor and which is the coupling constant of each one of them. So the motivations behind this work are, first of all, that since we are working with a deep learning model, once this model is trained, the characterization of these nuclei is very fast. And this is particularly very useful when you want to characterize a system of, for example, an MV and these carbon nuclei for quantum networks, etc. Another thing that we have been recently doing is to get in contact with a group of experimental researchers in Stuttgart in the Center for Applied Quantum Technology, and they work with these kind of sensors and signals, so it's very useful to have this communication. And this work started because there is a paper, which is the predecessor of this work, where they worked in a similar problem, but their method was based in the peaks that we see in the signal only in high magnetic fields. So the idea of our work was to extend this problem to lower magnetic fields too, and well, the approach is different.
Here, the motivation of this is quite synthetic logical, right? I would say.
Yes.
Because the idea is that, so I mean, if the industry is able to produce these chips, essentially at the industrial level, right? Many, so they would, if I'm correct me if I'm wrong, so they would send signals, which and then you will receive a lot of data, so that you can for each ND on a certain sample, right?
Yes.
So you are able to characterize how many available resources you have around, so then you have characterized your chip. Which means that you can construct neural code, essentially networks for communications.
Yes, well,
for memories or
for yes, for quantum computing there are other things that they do. I don't know if
I would say that maybe for memories or repeaters or these things, that would be no?
Yes. The thing is that if you want to characterize a large batch of sensors, nuclei, etc., there are other methods to characterize these signals, but they usually take longer and they are maybe more complicated, more expensive, I would say. So this is like a more automatized way of doing this.
The group in Stuttgart didn't mention a specific application yesterday.
No. Well, they wanted, from what I know, they wanted to do a similar thing to what I have mentioned here, this characterization. But what I have referenced here is another paper that they wanted to do something like this. But in Stuttgart, I think the idea is quite similar to this one. There are other applications, for example, in industry and all of that, but well, this is another thing. So more or less, these are the main motivations of this work. So I'm going to start by presenting the CPMG sequence. I don't know if you all know this sequence, but we have this Hamiltonian where we have a microwave driving, and if we go to an interaction picture with respect to this driving, we are able to apply some pulses to the MV sensor, and we can build sequences such as this one, which consists on applying pi pulses to the MV with a time delay between these pulses of 2 tau. In this way, what we obtain is this Hamiltonian where we see this f of t function. If you see right here, this function is 1 or minus 1, and this changes every time we apply a pi pulse to the sensor. So we have this square function. So applying this sequence, what we can obtain is the probability of the sensor being in the initial state after this sequence, which we have called P of x, since the MB is initialized in the x state. We can calculate this probability for different values of tau, which you have seen that tau is half the time delay between two pi pulses, and luckily there is an analytical expression to calculate this probability, so this makes it much more easier, faster when computing, especially.
So
yes.
These are the results of the Korean paper, right?
Well, there were previous papers that used this and derived these expressions. Okay. So it was before this.
And that one is valid for any value of the magnetic field?
Yes. Yes. In this case, there are no like important big approximations other than putting the sensor in resonance with in two states and all of that, but that is a typical thing.
Paper, so although they have this expression, they never explored the case of low magnetic fields.
No, because their method was not thought to be applied in signals of low magnetic field because of the shape of this signal. Because they based their work on these peaks that you only see in high magnetic field but not in low magnetic field. So
this is not a limitation in our case. That's not
no. In principle, no, because we have seen that it has worked, and there is no restriction to this shape of the signal. So yes, what I was saying is that having analytical expression is especially important, or because when you are working with neural networks, you want a very big batch of samples, you want to run a lot of signals, a lot of these probabilities, so this makes it much more faster, easier, and all of that. So now we come to the neural network, which first I'm going to present the input of the neural network, which is what we give to the neural network. In this case is this CPMG signal of the probability versus tau, this plot, and we have defined n as the number of pi pulses that we apply in the sequence. So in this way, we are going to use two different signals as the input of the neural network. One of them has 32 pi pulses and the other one has 256 pi pulses. We have used a different interval of tau for each one of them. This is just a convenient for different reasons. But the thing is that we have seen that for these specific cases, we get like a more continuous, more information about what we want to obtain, that we will see later on. So what we have done, as I said before, is work in both high magnetic field and low magnetic field, and this is more or less what we will see in this kind of signals. Here in high magnetic field we have in blue what I mentioned before of the two different pulses, N32 and 256. So this one is the 32 and this one 256. And as we can see here in the high magnetic field case, we see these peaks that I mentioned before, and when we go to a lower magnetic field, this gets kind of messier, noisier, or I don't know how to call it. Well. So the idea of the neural network is to take a batch of samples, and in each one of these samples we consider a random number of nuclei between 1 and 10 with random values of coupling constants A and B. These A and B are the components of the coupling constant, the vector A that we saw in the Hamiltonian. A is the parallel component and B is the perpendicular component. We have taken these ranges of A and B, which are from A from minus 50 to 50 kilohertz and B from 2 to 82 kilohertz. And once I have presented the input, what we give to the neural network, now this is what the neural network gives back. So this is the output of the neural network, which is a grid of size 100 times 80 kilohertz. And here we represent each of the nuclei using a two-dimensional Gaussian function. So these are Gaussian functions, and we have in one axis P and another one A. So the idea is to extract the mean value or the center of this Gaussian, which is going to be the exact value of A and B.
What does negative kilohertz stand for?
It's just I don't know how to explain. Doesn't have any physical meaning other than I don't know. Doesn't have.
It's a kind of interaction that can both increase the energy of your spin or lower it. So that's the reason it's applied, it's positive or negative.
Yes. There are also negative values for B, but we are not considering because of the symmetry of this signal, negative and positive values or B equal to the same signal, so it gives the same result. That's why we take only positive values on B and both negative and positive values of A. But you can take any real value.
So A and B are like the coupling strength.
Yes.
Okay. So it's not a frequency, it's just that you are using hertz to measure the coupling, right?
Yes.
Okay.
And yes, the thing is that we are using only two components because you can apply a change of basis every time, so you get only two instead of the whole vector A. So now, this is what the whole neural network looks like. We have these two inputs that I mentioned before, which are two different independent signals, and in each one of them we have plotted or used 1000 values of these probabilities, and then we insert this into the neural network, we train the neural network, and we obtain an output that looks something like this. In this case,
so
we...
inputs is the average value there, right? So that signal is discrete in some way?
Yes, it is an array of probabilities. Here is, well. And well, in this particular case, we have used an array of 71 times 57 size, which means that the pixel size is this number of kilohertz, but this is just what we have seen so far that works best in the neural network. But you can make this grid larger, smaller, and so on. Well, and now this is like the inside of the neural network. So we have first, after the inputs, we apply these convolutional layers. I don't know if you have seen when you want to make an image recognition neural network, usually people use two-dimensional convolutional layers. These layers are some kind of filters that you apply to these images, and you can extract information about this, the texture, the edges of a person or whatever from these images. So translating it into a one-dimensional convolution layer, in this case we have, as I said, an array of probabilities, but this probability has some continuity, some upper, lows, peaks, and all of that. So these filters kind of analyze this pattern, this tendency of the signal. And once we have taken all this information, what we do is to apply a flattened layer, which basically takes all the variables and puts them in an array. So doing this thing in the two cases, we then put these two layers one next to the other, and we want to take all this information and transform it into the output that is the image that we saw before. So for this, we use some dense layers, which basically connect all the information from here to the output and to obtain this. One thing is that what you have seen before is a two-dimensional image, but in reality, this output is a one-dimensional array. So the whole neural network is one-dimensional. The thing is that when we obtain this array, we reshape it into the image that you have seen before, but to make this clear that there is no two-dimensional layers or anything.
So the array is the activation function.
Yes. Well, I'm not explaining this in very much detail because this could take very long. But yes, all these that you see right here are normalization layers. Well, they are quite typically used in convolutional layers, but this is more like technical details about I don't know. I thought that it would not be very interesting, but I don't know. So what we have now is, well, from in the past few weeks or so, we have worked only in low magnetic field because we saw that the behavior is very similar in high magnetic field and in low magnetic field. So I'm going to show you only the results in low magnetic field. And once we have trained this neural network, we want now to test this network. So what we do is to take some samples that the network hasn't seen before, and we give them these samples to see what they give back. So what you see right here below is the true value of the samples that we give the neural network, what we ideally would see, and here we see what the neural network predicts, which, as you can see, is not perfect, of course. Here, in some cases, you can see that there are no clusters, but we can see, there are no Gaussians, but we can see some kind of clusters and some noise over here. And, well, this leads me to the next point, which is what we are currently working on, which is to make a post-processing of these images to get rid of this noise and to basically calculate the mean value or the center of these clusters, which will give us the values of A and B, and we will be able to compare to the true values to make some statistics and all of that. Another thing that we are considering now is dipole-dipole interactions that we have so far neglected, but we are trying to incorporate that into the work, and we are using a method called clusterization. And since we have been in contact these past days with this experimental group in Stuttgart, we are trying now, starting to make more realistic signals, for example, adding noise, the coherence, and all of these things that are necessary for real data. And that is all. Thank you so much.
One question about this last part that you are going to work on. No, keep the. This last thing about obtaining the results from the output of the neural network. What are you trying to do? Like a numerical, like a numerical algorithm, another neural network.
There is well, in Python there is an option called OpenCV, which is basically an algorithm. It's not a neural network, it's just an algorithm to like pre-programmed. You have not to do many things, but yes, basically extracts these clusters, makes this difference, and it can give the mean value, the deviation, and all of these things. But Estival is working in this part of the work, so I don't know very much about it.
Yeah, because this problem about getting like some data from a map that you don't know really well what it means, and you have some edges around the nuclei and stuff. This is very similar to the problems that they have in thin layers, thingy stuff. Usually the same problems.
Okay.
So then, for example, can we
go back to the slide in which you show essentially this data. No,
This one.
Previous. Wait, no? Yeah, there. Right? So essentially these are the kind of signals you are using to train your neural network, right? So in idea, okay, I can imagine your neural network has something special, right? That it's a bit different from previous that we have tried, right?
Well,
This is my second question. The first one is, so which other numerical methods can we also use to analyze this signal without, I mean, why we have to go to neural networks? Which is the main point there?
I don't know much about the other methods that are used for this. They are
trendy in
based
some way,
on
right?
yes, Fourier transforms and all these things, I think.
But do you think they will work here or not?
I don't know if these methods are used in low magnetic field, but because from what I know, they usually are based on these peaks of the signal.
Essentially, one needs to fit a signal, right? With a certain number of parameters that one doesn't know, right? And for that, there are different, I guess, statistical methods based on numerics and Bayesian theories or whatever, right? And when neural networks do you think enters here?
Because first of all is the thing that they work very fast and you can obtain data. You can, for example, what I said about testing the neural network after you have trained, you can test, for example, 10,000 samples in 30 seconds, some of that. So if you want to do that, doing calculations alone, all of that, you will spend much more time doing this. And I'm not sure if, because we don't know yet what precision, what is the number of nuclei that the network will be able to determine. So we don't have like an exact number of this precision of this number of nuclei. So we are not able yet to compare one algorithm to the other because there are not like proper statistical measures done.
So for the moment, we can say that it is fast compared with others.
Yes, and it seems precise.
I think the speed is the main one. You can probably make a lot of work, fit a lot, use an inlet or whatever, and get a really good fit, but it's going to take you a lot of time. This is going to wait in 15 seconds for that.
So one thing is it is quite flexible and fast, right? That would serve for
And you don't need to think that's data.
Okay, and your neural network has something special regarding other trials.
One thing that we did because we saw that worked basically was to what I'm showing you here is the signal, the original signal, but then we do like a normalization of this signal. So because I don't know if you have seen here that we use these batch normalization layers which normalize these signals with the mean and variance when it's just a normalization. So we saw that normalizing this input signal worked best somehow. There's no like a real explanation for that, or I don't have it, al menos.
Because previously we were trying some, let's say, some spectra, right? And we were analyzing it and wanted the numbers, right? Of let's say the value of the parameters that generate that, right? But here the architecture is a bit different, right? Because in some way we can also tell you how many we have without having to, right?
Yes, also, I don't know if you refer to this, but in other approaches, what they do is a regression, which is basically instead of building this kind of image, what they have done, what I have seen, is to put as the output of the neural network these values of A and B and make the neural network guess these values. So this is kind of a different twist to this output that is independent of the number of nuclei, because if you, for example, want to detect two nuclei, you need, for example, 4 values, so the output of your neural network should be 4. If you want to have 3 nuclei, it should be 6. So you have to change the output every time you change the number of nuclei that you are working with. And most of the time you don't know how many nuclei there are in a sample, or it's very common. So this is kind of a blank paper where you see spots, and they can be 4, they can be 6. Or
So they are telling you yes or no in each spot?
Yes.
That's what your neural network
Yes,
says?
it's what we were talking the other day that Carlos said, that is kind of a pseudo probability where you can find in this space the nuclei.
And in the approach of the Korean paper, they can also, is also valid for an arbitrary number of nuclei, or
What they did was to take each of these peaks and extract if if these peaks corresponded to 0, 1, or 2 nuclei.
Okay.
But first of all, they obtained this value of 0, 1, and 2, and then they had to do like a regression to obtain which coupling constants the nuclei have.
Okay.
Yeah, they can detect many nuclei, but they track these peaks which appear like.
Which is not.
There are like 2 parts of the neural network.
And then, okay, in our case now we are fighting with the, I guess, with the precision thing, right? Which is
Yes.
having the analysis of these images, right? The pixels.
Yes, to know exactly like what are the limitations of this approach and what are the good parts.
There is this funny fact that the network is able to generalize.
I didn't mention that. Yes, well,
That you can train the network to only see up to 4 nuclei, and you give it 6, and it's able to root 6.
Yes.
So it's like mirroring the inner pattern.
I don't know if I have. Yes. What I have seen recently, I don't know if I have any example here, but I have trained usually up to 10 nuclei, and I have seen that the neural network generalizes up to 12, 13.
Okay.
Without, I mean, I think that the most interesting part is that it generalizes other than the number of nuclei more that it captures. Because yes, the thing is that it's learning a pattern that seems to be kind of continuous from 1 to 10 and so on.
So that's something that we cannot see, but apparently they can see, right?
Yes.
It's like it has found a method to extract one nuclei from the signal, whatever it looks like, and put a spot. But you said it shouldn't? No. I mean, it's nice that you can do it, but it's not quality that it's going to generalize that. But generally, numerals, once it gets made, it can generalize to increasing. It can generalize, but it's not quality. So it's like it's
We have seen some cases, but it's not like always happens.
And what is the x-axis in
The tau, this, maybe you can see, this tau is, you remember this? In the sequence, this distance between pulses is 2 tau. So changing this distance, maybe
it's
larger
time,
is more.
right?
It's time, yes.
So, just a random comment that have you used any other neural networks that are not convolutional? So maybe recurrent neural networks? Because recurrent neural networks are good with time series analysis.
In the beginning, we experimented with some other neural networks. We tried some LSTM.
Yes, so let's say that we can use here.
We did like some testing, but we didn't get
one-dimensional evolution were the ones
Yes.
that work the best.
Okay, and the other question, have you read any other activation functions that are not the sigmoid or lineage? You have?
Yes.
I don't know.
Many. Yes, yes.
And this is the best, really is the best.
I would say yes. I haven't tried any combination possible, but I have tried many combinations. And yes, yes, yes. And yes, and another thing that I didn't tell, but we are also considering maybe working with other type of sequences because, well, each sequence has its limitations. There are maybe nuclei that you cannot differentiate because of the nature of the sequence. So working with other sequence or maybe combining different sequences into one neural network will give like a broader information or like more extended information about all these parameters. But yes,
This
for
is
now,
super nice because it's so simple to experimentalize like
yes. But then the other day, the experimentalists told us that they are working also with other sequences. So we said, okay.
Something like a software is also is versatile regarding the number of measurements or whatever is that algorithm. It's implemented, say, okay, this is going to predict what happens where each value is 100 shots or from 100 to 1,000, right? And give you, I don't know if this is able to predict.
this current neural network wouldn't work like that. It would get confused, but from there you have probably better structure.
Yeah, the balance and really change the okay.
Have a question. Now that you are having, you said like one interaction between the nuclei, like, how do you do that? Because now, for instance, for the case of 250 nuclei, there are like, okay, so how many nuclei do you consider? How many?
For now, I have only done some like little tests which are considering, for example, one cluster of 2 or 3 interacting nuclei. I do that.
Like for instance, you have 10 nuclei interacting among.
Well, what I say is that in a real sample, you would have most of the nuclei non-interacting with each other and maybe a cluster of 2. So what I am testing now is these specific clusters, this interaction if the neural network lets. So I suppose that generalizing this cluster with other independent clusters that have worked so far will work. But this is just the first like idea that we have of this classification.
Yes, and it would be like possible in time because there are a lot of combinations.
Yeah. Because what you do is if the typological interaction between them is not so strong that we're going to see in the sequence, you just cut it, and then you make like independent little spaces which are much simpler.
Of course, we have to rely on the numerics, but it's a bit analytical, a bit numerics, right?
Yes, you can treat.
So for instance, you cut like, at some point you cut and you say from now on they won't be interacting with the first. Okay.
And that's some analysis for Cambian, because you know the finite number of sequence, and for example, interaction between one and your sequence is milliseconds, essentially you never know.
Yes.
You would have something like this, for example, you can treat this, this nuclei as I have treated this with this expression because this M corresponds to each one of these clusters. So you can calculate the M of corresponding to this independent nuclei using this expression, but then when you have interacting nuclei 2, 3 or whatever, you have to calculate this numerically because there is no analytical expression so far. Eso es.
To us. Maybe there is.
Maybe there is, but we don't have it yet. So,
It's not so.
but it is not fully numerical because you have this advantage of having this kind of you can separate into clusters and treat independently each of the clusters.
So that method, if I'm not mistaken, works only. I think I wrote some notes on that. Right? I gave you some notes regarding the potential approximation. But, I think that works very good in the case where the classes are strong enough. But I think that's not right. Yeah, it's 10 megahertz or whatever is already difficult. So, yeah. So this is very, let's say, fast compared with the Laravel, as we are exploring the low frequency. That's yeah. So it will be
But an integrated expression like that, but with interaction would be possible or not?
We haven't found it, but I think we have used with two.
Yeah, we do what?
Two streams, we try to level interaction between them. I think maybe we can get that.
but maybe yes.
I tried in Mathematica and it cracked. O sea que nada. But I haven't tried anything else, so
So if your input sequence is generated by some coupling that is out of the scope of your neural network, have you tried that? What kind of prediction does it produce?
to detect a nuclei out of this range of coupling constants, we haven't tried that. Because, well, mainly because you have to, it's not that easy because you cannot change the output, the shape of the output and the input of the neural network.
Keep the output, but change the input.
Yeah, so that's the neural network. Like try to predict some coupling or just give some random
I haven't
trial
tried.
what happens if you introduce
haven't
a
tried.
wrong input.
Yes, maybe one that could be over here.
We have to extend this range now. They have us to try up to 100 kilohertz, so I think that's a nice opportunity to see what the network does.
Yes.
I have a pragmatic answer to that, right? Because typically, to have something which is very weakly coupled, it's not really a problem because probably you cannot identify, you cannot even use it, right? However, you have something which is very strongly coupled, probably is really obscure the rest of the presence of the other mechanisms. So when we analyze this, we say, okay, I cannot analyze this, but probably because of this, I cannot use it.
What do we get neural network say?
I don't know.
If an neural network tries to say something like
Yes.
what does it do?
Maybe random.
I know. I can try to see it. It's very easy. The thing is that you don't give a chance to make it right because you are not including these rates. For example, in the case of having more nuclei, you give the change because there is space here to put more nuclei. So, but
I mean, is that you have tested and you have spit out giving correct input and obtaining a correct output. What I mean is, if you give an incorrect input, you should obtain something that is incorrect or at least not correct.
yes, the correct thing would be to not put this nuclei, right? Because if it's out of range, there should be nothing here. Yeah, that is the correct thing.
I don't think it's going to do that.
Pero vaya.
I think it's going to random stuff.
Yeah, something which is strongly coupled, the problem is that if you have something which is very strongly coupled, probably another method to say, okay, this is an source.
Or I mean, noise or something like that.
Noise is not, in normal conditions, maybe it's not really a problem, but but if there's something which is strongly coupled, right, probably the dynamics is simple somewhere, right? You can say, okay, here we have something, imagine that in the worst case, probably this is not going to observe these things, and I can say, okay, that's, if I hit the signal, I say, there is some element which is actually capturing all the information. That could be a potential solution, but it's if it is automatically,
Some kind of like a prefix that is going to the neural network to check first if there is something.
but if everything is automatic, it's not much of a trouble.
I will try that later and I will tell you. Porque me ha entrado curiosidad. Okay.
Thank you.
One question. This is like the scheme theory that you have two averages of 1,000 inputs and then you send them to the neural network, but only the average, or you have 2,000 graphs that you
No,
send to the neural network?
this 1,000 means the number of points in the plot. Then you give many of these samples to a neural network, hundreds of thousands.
Oh, okay.
So this is just like
One
one
number
run
of
of
inputs is
the-
the number of thousands.
Yes.
That was the question. 2,000 inputs.
Yes.
But it's 2,000 inputs, but you have a lot of runs or a lot of copies of those that you fed into the neural network.
But yes, we'll see.
Okay, let us thank you. Speak again.